So here's a fact, a theorem actually. A homomorphism or a linear map is determined by its action on a basis. So if I have a homomorphism H that goes from V, the domain, to W, the codomain, and I have a basis for V called B, which is the set of vectors B1 to Bn, and I know where these basis vectors are mapped to from V to W, then I know what the entire action of the homomorphism is. That is, I know what it does to every vector in V. And intuitively, that should make a bit of sense because every vector in V can be represented as a linear combination of the basis vectors. So if I want to find out where some vector that is some linear combination of these basis vectors is sent to, I first look at where each of the basis vectors are sent to, put those results in that linear combination, and I should get the result. So specifically, if this is a basis for V, and then I have a set of vectors W1 to Wn in W, just any set of n vectors in W, not necessarily a basis. It doesn't even need to be a set of distinct vectors. If this is the case, then there will always exist some homomorphism, which we've called H, where each domain basis vector Bi is sent to a corresponding vector Wi in this set of n vectors in W. Specifically, that is going to be a unique homomorphism. So if I have a homomorphism that has this action, and I'm asserting that there is one that has that, I'm asserting that it exists, that's what this backwards E symbol means, then there's only one homomorphism that has this specific action. If I have this vector V in the domain V, then I can rewrite that as a linear combination of the basis vectors, C1 times B1 all the way to Cn times Bn. So if I evaluate H of V, I'm evaluating H of this linear combination. And because H is a homomorphism, I can distribute it to each of the terms in this linear combination and then pull out the constant. So this should equal C1 times H of B1 plus all the way to Cn times H of Bn. But H of B1 is W1, and H of Bn is Wn. And in general, H of Bi is equal to Wi. That's the action of the map as we defined it. We said there exists a homomorphism, in fact, a unique homomorphism that has this specific action between the basis vectors of the domain and this set of n arbitrary vectors in the codomain. And since the representation of each vector in the domain with respect to the domain basis B is unique, this map is well defined as long as we define this linear combination of the W vectors to be the output when we input the vector V into the function H. We can also verify linearity by showing that H applied to some linear combination of two vectors in the domain is the same linear combination of H applied to both of those vectors individually. This is really H of S1 times some linear combination of the basis vectors, which is equal to V1, plus the second scalar S2 times some linear combination of the basis vectors, which is equal to V2. When I represent V1 and V2 as linear combinations of the domain basis vectors, you'll notice I get for V1, C1 times B1, and a C2 times a B2 is implied next, and at the end I have a Cn times Bn, and similarly for the representation of V2 with respect to that basis, we have D1 times B1 all the way to Dn times Bn. So in particular, they have a certain constant multiplied by the first basis vector, the second basis vector, in general the ith basis vector in common between these. They have terms for each basis vector. So I can rewrite this as H applied to S1, C1 plus S2, D1 times B1, the first basis vector, plus all the way to S1, Cn plus S2, Dn times Bn, the nth basis vector. And of course, this is now just a linear map applied to a linear combination of these basis vectors, B1 to Bn, so I can distribute the application of H to each B1 to Bn term, and then effectively factor out the constant because scalar multiplication is preserved, and I get S1, C1 plus S2, D1 times H of B1, which is W1, plus etc. all the way to S1, Cn plus S2, Dn times H of Bn, and H of Bn is Wn. And that looks like this. I then distribute all of the C's and D's to these W vectors, and because of the rule of how this linear transformation works, the linear combination of all these W vectors multiplied by the C's is H of V1, and the linear combination of all of the D's multiplied by all of the W vectors is H of V2. So this becomes S1 times H of V1 plus S2 times H of V2. So we can see how H applied to a linear combination of two vectors in the domain with scalars S1 and S2 and vectors V1 and V2 evaluates to the same linear combination of the associated output vectors in the codomain. So now we know that this map exists, that it's well-defined, and that it's linear, and we just need to show that it's unique, that there is only one map of this kind. And we can basically intuit our way through this part. H has to be unique because any other map that associates each bi in the domain with each wi in a set of n codomain vectors will have the same effect as the original map H on the domain vectors, since they're all linear combinations of the basis vectors. And if two maps have the same action, then they're the same map. So there really is only one map that does this, and that's H.